This is my assignment. This is my submission to our assignment for heaps. So in this assignment, we've been provided binary node code. We are asked to create a linked heap, which is a minimum heap, with the interface of insert, delete. Delete will delete the pair with minimum key value within heap. Basically, this will be the root value, and then pick. Pick will return the minimum key, the key value pair with the minimum key value within the heap without altering the contents of the heap. And after that, we would need to deploy a priority queue that is backed by our linked heap. In implementing, we have to implementing add key values into the priority queue and remove from the priority queue and the minimum of the priority queue, and then check if the queue is empty, and then this is the length of the priority queue. So and finally we will have to perform the operation to showcase the working priority queue, which will be we enqueue the items into the with the order, and then we dequeue 3 items by priority. So here let's look at our code. So firstly, this is the provided binary code. It's not alternated. It is just as original. So it has element, parent, left and right. Had all this method here, get and set. Later on, we're gonna use this in our linked heap to create our minimum heap. So in our minimum heap, firstly, when we initiate this, we create this, we will have the root as none by default and size at 0. Then very important function here is this binary path. So here we have a tree structure. In order to keep track of every node in the heap, their position, we are using this unique binary path that is turn the index of one node in the heap into a binary number, so we can we will know the exact position of the node, and then which is the reverse side of the binary path, we will get one node, get the node itself by giving the path. So once we are giving the path and the index of the node, we would know which node it refers to. And thirdly, we have this swap nodes function. So here it is used in our heap structure mainly for swap parent and child in all the heap structure changing. Basically here we check all the possible cases that would happen, and to make sure the swap will happen successfully. And then we have another help function, which is the float node function. So float node is what we have to do when we insert a new node into the heap. So that is when we put the node into the right function, not the right position of the heap. We will have to float it to the right position of the heap to maintain the heap structure or the order. So it will keeps swap the new element and the new element and its parent element if the new element is smaller than the parent. So, and then we have another function, which helper function, which is the minimum child. basically this is given a node, and we find out the child with the minimum value. This one will be used in our sync node function. So sync node will be used when we delete um, from in our delete method of this heap, which is delete root of this from this heap. Sync node basically will just move the node down to the right position in order, and then maintain the heap order. So here, if we then we have the insert function. So we firstly check if the heap is empty. If it's empty, and it will just be the new node itself. If not, firstly we will have to know the path to the new node, and then we would then know, and then we will then get the parent. So we have to check where we should put our new node to. Once we know it, and we're gonna put it there, and then we're gonna float the node to its right position, and we're gonna increase the size of the heap by 1. Then we have the delete function. So firstly, same thing, we're gonna check if the node if the heap is empty. If it's empty, we're just gonna return, and then if not, we're gonna get the root node value, which is what we have to return when we delete it. And then we're gonna just have to remove the root node itself, and then put the last node. First, we have to find the last node, and then put the last node into the right position. Put the last node at the top, and then we have to sync the new root to its right position to maintain the heap structure. And then we're gonna decrease the size of this heap by 1, and we're gonna also return the new root value. Then this is the requirement function method we have to build here. It's a peak. So by definition, we're gonna just return the root of this minimum map heap, and then it's the length of the heap itself. We're just gonna return the size, and then this the string functions here in order to print out the things we need here. After we construct our heap linked heap class, we're gonna construct the priority queue class data structure using the methods from our linked heap. So here, when we create this priority queue, we're gonna have a linked heap created. Then we have the add function here. So this add, we're gonna just using the method from heap, the insert method, and then we're gonna print it out what we've inserted here. Then the remove method, which is just utilizing the delete method from a heap. Minimum is the peak from our heap, and it's empty. We're gonna just check the length of the heap, is it 0 or not. Length of the priority queue, it will just be the length of the heap itself. So let's see, we create this priority queue class, and then we check if it is empty when you create it, and check the length. So it's empty 1, and the length of queue is 0. Then we're gonna just enqueue the items using the add method. So it's we're gonna just add the key here, 11 7 8 6 5 9 4, and then we check if it's empty, and it is not, and then we look at the length of the queue. So it's 7, the right length, and then we're gonna just dequeue from the priority queue. We gonna just use the remove method here. So we remove 3 times by the priority. So the first, and then check what had been DQ'd from the DQ. So we have 4, 5, and 6. So by the this meet our requirement and in the right order. And then we check the length of the queue, and it is 4. So um, our priority queue is working perfectly. Thank you, Professor.